Whenever IEEE says graph, what they mean is a mathematical structure used to model pairwise relations between objects. A graph is made up of nodes and edges, and sometimes people call the nodes vertices. So if you read another source and it's talking about a vertex and an edge, vertex means node, node means vertex, it's the same thing. Graphs may be directed or undirected. A directed graph just assigns a direction to one or more edges. Exercise 1, name at least 3 real-life applications of graphs and draw small examples of each. So one application of a graph might be a map of train stations. Okay. Suppose I have a few train stations, and they are going to be connected by train tracks. So the trains can get from one to the other. This is a graph where all the nodes are train stations. And the connections between them, the railways, are the edges. So that's 1, 2, 3, 4, 5 nodes and 4 edges. That's an example of a graph. What's another example of a graph? How about social networks? Let's say this is a social network where maybe this guy has 1, 2, 3, 4, 5 friends, and these 3 are all friends with each other. This person only has 1 friend. Right? So maybe your social network looks like this, where every edge represents a friendship, and every node represents a friend. That could be a graph. Carter, what's another distinct idea that could be represented as a graph? Graphs are all over the place. You just gotta think hard enough. I'll give you another one, because I used to work in a refinery, and so one of the things that can be and should be modeled by graphs is like if I have this node, it might represent like a chemical reactor, and I could have a directed graph that shows feedstock going into my chemical reactor. Like maybe this is a hydrogen stream, and this is a, I don't know, a distillate or a furnace oil stream. Furnace oil is what you call unfinished diesel. But maybe I mix things together in my reactor, and then they go out of the reactor into another vessel, and that vessel separates some light-ins from the liquid. So this is like a vapor and liquid separator, right? And perhaps the vapor goes back to maybe a hydrogen compressor and loops back around, and maybe I have some makeup hydrogen, and maybe there's another node here where I have some purge hydrogen. And the liquid might go to a distillation column that separates it into several other streams. Okay, so this could be a chemical process. And in a chemical process, Each one of those edges represents like a steel pipe that has material flowing through the pipe. Okay? Uh, for this reason, this would be a directed graph. I told you graphs could be directed or undirected. In a social network, you hope that your graph is not a directed graph. In a social network, you hope that the feeling is mutual and everyone is friends with each other, right? Like this would be like Facebook. If it were Twitter, I guess it would be a directed graph, right? Because can't you like, I don't know how Twitter works, but you follow somebody, but they don't necessarily follow you back. If that's the situation, it would be a directed graph. But if it's a mutual thing, like on a Facebook social network, you have to be friends with each other, then it would be an undirected graph. But this is a directed graph, and the only difference is I draw little arrows to show you which direction the edge is going. It's going from this node to this node. So graphs can represent trains, they can represent social networks, they can represent chemical processes, they could represent electrical circuits. Graphs could be like the human circulatory system, right? The edges could be distinct arteries, veins, and the nodes would be the branches of the arteries and veins. Yeah, that'd be pretty complicated. Another type of graph, if you're keeping up with all the AI stuff, is like a neural network. You can represent a neural network visually as a graph with all the edges and the nodes. Won't go too much into that. But there's a lot of vocabulary terms that go with graph theory. A self-loop is an edge in a directed graph from a node to itself. Parallel edges occur when more than one edge goes from one node to another. So I'll draw you a graph. Let's say this is a directed graph. So these would be parallel edges, and this would be a self-loop. So we might make the distinction between a simple graph, and a simple graph is an undirected graph that has no self-loops and no parallel edges, and a multigraph. Honestly, a multigraph doesn't tell you very much. It's not a very good vocabulary term, because it just says you are allowed to have direction, self-loop, and parallel edges if we're talking about multigraphs, but you're not allowed those with a simple graph. Exercise 2 would say draw one example of a simple graph and one example of a multigraph. Well, we've already kind of done that. Here are some simple graphs. And then there's a multigraph containing at least one self-loop and at least one instance of parallel edges. Okay. The degree of a node is the number of edges connected to the node. So the degree of the node is the number of edges connected to the node. So AJ, what's the degree of this node? Yeah, so like I said, the degree of the node is the number of edges connected to the node. So the degree of this node would be 5. And the degree of this node would be 3. 1, 2, 3 edges connected. The number of edges connected to our particular node is its degree. This theorem says the maximum degree of a node in a simple graph with n nodes is n minus 1. because a simple graph cannot have any parallel edges, and it can't have any self loops. So if I have a graph like this, where n is equal to 1, 2, 3, 4, 5, the maximum degree I could have for a particular node is if I have an edge with every other node. Every other node would be n minus 1 nodes. That's why the maximum degree is n minus 1. If I had a multigraph, there is no maximum degree, because I could keep adding self-loops, or I could keep adding parallel edges. I can make that as high as I want, but for a simple graph, that's how it goes. A complete graph. I told you there's a lot of vocabulary. A complete graph is a simple graph in which every node is connected to every other node by an edge. It's as connected as possible. The maximum total number of edges in a complete graph is n times n minus 1 over 2. The best way to think about this, if you want to explain or prove this theorem, is to start by considering a directed but otherwise simple graph. And I guess what I mean by that is no parallel edges and no self-loops. But I'm allowing myself to have direction. That means if I put all my nodes around in a circle, every single node can have an edge directed away from it. So each one of n nodes has n minus 1 directed edges to contribute. So for a directed but otherwise simple graph, being as connected as possible would yield n times n minus 1 directed edges. But what we're talking about here in this theorem is a complete graph, and a complete graph is simple. And so in the simple case, one undirected edge is equivalent to 2 directed edges. Right? Because instead of requiring me to have an edge that goes from this node to this node and this node back, we could just call it one single undirected edge, right? And so we divide the number of edges by 2, and we end up getting n times n minus 1 over 2. So hopefully not too difficult to understand here, but the maximum total number of edges in a complete graph is n times n minus 1 over 2. Some more vocabulary words. We say that a simple graph is dense if most of the possible edges are in fact edges, which means I'm calling it a possible edge if you look at any two nodes. Any pair of nodes on the graph could have an edge between them. And if most of the nodes are connected, most of the pairs of nodes are connected, we would say that's dense. And if most of the pairs of nodes are not connected by an edge, then we would say the graph is sparse. Density ranges on a scale from 0 to 1, and the density of a simple graph, which means it's not directed, that has m edges and n nodes, has this formula. This is the density of a simple graph. Exercise 5 says, explain why the density has to be greater than 0 and less than or equal to 1. So D is greater than 0 because there should be at least one edge. Why does it need to be less than or equal to 1? Because what we're doing for density is we're taking m, which is the number of edges, and we are dividing by the total, the max total possible number of edges. In other words, we're taking m divided by n times n minus 1 over 2. So to divide by a fraction, you multiply by the reciprocal, and that's how you get 2m over n times n minus 1. So now you can calculate the density of a graph. Where does it sit? On a scale from 0, where it's barely connected, and 1, where it's completely connected. It's never exactly 0. The density of a directed but otherwise simple graph with m edges and n nodes is this. So when I say directed but otherwise simple, I mean that there's no self-loops and there's no parallel edges. But it is directed. The only difference now between this formula and the previous formula is that there's not a 2 in the numerator. Because when you say you're allowed to have directions, now you can have twice as many edges. You can have an edge going that way and an edge going that way. Twice as many edges, right? So same reason. But now when I divide by the max possible total, that's just n times n minus 1 for a directed graph. Okay, so kind of switching gears just a little bit. If I say matrix, I'm talking about an array of numbers where the entries are arranged into a grid with rows and columns. The size of a matrix is always given by two numbers, the number of rows and the number of columns. And we say a matrix is a square matrix if the number of rows and the number of columns is the same. Typically, we use a capital letter to represent a matrix and the corresponding lowercase letter to represent entries in the matrix. And we say a matrix is symmetric if it's a square matrix, and if I swap the index of the row and the column, I get the same number. So for each matrix, determine its size. If I look at this matrix A, I would say that the size is 3 by 3 because there's 3 rows and 3 columns. The requested entry is 1, 2. That subscript is the row index, comma, the column index. So this is row 1, column 2. And determine whether it's square and symmetric. It is square. Is it symmetric? It is not symmetric. If it were symmetric, we would see this be a 5 and this be a 5, and that would be a 1 and that would be a 1 and this would be a -2 and that would be a -2. All the entries would be a reflection across that diagonal that goes from top left to bottom right. What about the next one, matrix B? This has a size, Dario, what's the size of matrix B? 9. Maddie, what's the size of matrix B? 3 by 2, you got it. 3 by 2, 3 rows and 2 columns. Is it square? Not square. If it's not square, it's not symmetric. You can only be symmetric if you're square. And Matthew, what's entry 2, 2? -1. Okay, and then this is my last example here. Let's say the size is 4 by 4. It's square. Antonio, is this symmetric? Yes. It's symmetric, and notice we don't care what's on the diagonal. The diagonal is this entries that go from top left to bottom right, 4, 3, 2, 1. Doesn't matter what those are. What matters is that the entries on either side of the diagonal are the same across from one another. So this is a 0 and a 0, 0, 0, 1, 1, 1, 1, 0, 0, -1, -1. That's what makes it symmetric. All right, Antonio, what's the entry in row 2, column 4? 0. So the C24 is 0. Questions? No? All right. The adjacency matrix of an undirected graph has rows and columns that represent the nodes of the graph, and the entries of the matrix are either 0 where there's no edge or 1 where there's an edge. Okay, the rows and columns of the matrix represent the nodes of the graph. The rows and columns of the matrix represent the nodes of the graph. Okay. So what this means is that if I'm going to make a matrix for this graph, it has 6 nodes, it's going to have 6 rows and 6 columns. Because there's 6 nodes. So I'm going to have a 6 by 6 matrix. In the first row, I'm going to have a 0 if there's not an edge and a 1 where there is an edge. So it's going to look like this for the first row. In the second row, I'm looking at the second node, and I'm going to put a 1 where there's an edge and a 0 where there's not an edge. So it's going to be like this. In the third row, I'm looking at the third node of the graph. I'm going to put a 0 where there's not an edge and a 1 if there is an edge. Fourth row of the matrix, so I'm looking at node 4. It only has an edge with node 3. The fifth row of the matrix, I'm looking at the fifth node. It only has an edge with 1 and 6. And then the sixth node makes up the sixth row of the matrix, and it's going to have edges with 2, 3, and 5. So this is my adjacency matrix. And it doesn't matter whether you look at the rows or if you look at the columns, because this is an undirected graph. So if, for example, node 3 is connected to node 2, that means node 2 is connected to node 3. And you notice that the matrix then is a symmetric matrix. You could also do this in the reverse direction, where if you give any matrix that is a symmetric matrix with only zeros and ones, then you should be able to recreate a graph, an undirected graph, that represents the adjacency matrix that you just randomly came up with. So there's a one-to-one correspondence between, well, I shouldn't say a one-to-one correspondence, that's not true. There's a relation here between simple undirected graphs and symmetric matrices with zeros and ones. I say it's not a one-to-one correspondence because I could have numbered these nodes any way I want to, and I would have had different rows and columns. I would permute the rows and permute the columns if I chose to number these nodes differently. So the order in which you place the nodes matters, I guess, when you're drawing up this matrix. Okay, any questions about how we did that? Super clear?
Surprisingly no.
Okay. Now we're going to do the same thing, but for a directed graph. We're going to do an adjacency matrix for a directed graph. The difference when it's directed is that now we have these little arrows instead of just line segments, and the rows of my matrix are now going to represent the origin of every little arrow, every edge. And the columns are going to represent the destinations of the edges. So these will not be symmetric. Because the graph is directed. Okay. Write the adjacency matrix corresponding to the following directed graph. Okay. Looking at node 1. Node 1 is the origin of two edges that go to 2 and 4. Node 2 is the origin of an edge that goes to 3. Node 3 is the origin of edges that go to 2 and 5. Node 4 is not an origin for any edges, and node 5 is an origin for an edge that goes to node 4. So notice this adjacency matrix is not symmetric. Because it's a directed graph. And again, if I give you an adjacency matrix, you should be able to recreate the directed graph corresponding to it. And there's almost a one-to-one correspondence. The only difference is if I numbered these nodes differently, I would have to permute the columns and the rows, but otherwise the same. The columns still represent nodes 1, 2, 3, 4, and 5, except if you look at the columns, you're looking at, is this node the destination for any edges? And like node number 1 is not the destination for any edges, so it's got a column of all zeros. Node number 2 is the destination for edges 1 and from 1 and 3, so it's got a 1 and a 3 here. That's how you read the columns. By the way, the reason this is important is because if you and I sit down to think about a train station or a social network or a chemical process or an electrical circuit or, right, a billion other things that can be modeled by graphs, you and I are going to have an easier time drawing this picture. But how do I store this picture in computer memory? Exactly. Computers just store arrays of numbers, right? In this case, it's just an array of bits, so that's pretty memory efficient. But if you're going to be a computer scientist, you need to know how to communicate the structure of a graph to a computer. That's why adjacency matrices matter. So the next thing is called an adjacency list. We can again make these for undirected graphs, and we can make these for directed graphs. I'll show you examples, but the adjacency list of an undirected graph is going to have n nodes and n entries. Each entry is a list of the nodes to which it is adjacent. So let me just do that first part for you on this undirected graph. So the way this works is I look at node number 1, and I would say it is adjacent to nodes 2 and 5. Then I look at node 2, and I say it is adjacent to 1, 3, and 6. And I look at node 3. I say node 3 is adjacent to 2 and 4 and 6. And I look at node 4, and I say that is adjacent to node 3. And I look at node 5, and I say that's adjacent to 1 and 6. And I look at node 6, and I say that's adjacent to 2, 3, and 5. That's kind of the first part. The second part of this is when I put this into practice on a computer, I'm going to store 2 arrays. In other words, 2 lists of numbers. The first one is going to contain just an ordered list of all of these adjacent node numbers back to back. And then the second list is going to contain the locations at which I switch to the next node. So let me show you an example, because I'm sure that sounds like crazy. But how do I convert this into computer speak? I would make one list that says 2, 5, 1, 3, 6, 2, 4, 6, 3, 1, 6, 2, 3, 5. I can store that list in computer memory. We'll call this list E for edges. And then I'll have another list, I don't know, I might call it N for nodes. And this is going to be the list that says 1, 3, 6, 9, 10, 12, 15. Sorry, I don't need the 15 at the end. That's my bad. And what this is telling me is that as I look at my big long list E, node number 1 starts in the first position. Node number 2 starts in the third position, right? So that means 1 and 2 are the first two entries in my longer list belong to node number 1. And if node number 3 starts in my sixth position, then node number 3 starts at 1, 2, 3, 4, 5, 6. Node number 3 starts with this 2, 2, 4, 6, right? Node number 4 starts at position 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Node number 4 starts with this number 3. Node number 5 starts in the 10th position. So that starts with the number 1. And then node number 6 starts in the 12th position. That's where I get the 2, 3, 5. So E is the list of node connections, and N is a list that tells you what position to look at in E to start getting the numbers for a particular node that you're interested in. And again, we're talking about how do I communicate the structure of a graph to a computer. If we care about things like train stations and social networks and chemical processes, how do I communicate that with my computer? How do I write this in a program? Well, I'm going to have to store numbers like this and have a way to access and read those numbers. Okay, moving on to the right side of the page where I've got a directed graph. The adjacency list of a directed graph is slightly different because I'm only considering the ones that are the source of the edge. Not the destination, but just the pre-image, if you will. So like for the number 1 node, that's a pre-image for 2 and 4 in this graph. For the number 2 node, it's only a pre-image for 3. I'm not going to put 1 and 3 down for my directed graph because I'm only concerned with the node it originates from, the node that the edge originates from. So 2 gets 3. 3 gets 2 and 5. 4 gets nothing. And 5 gets 4. So if I'm going to communicate this to my computer, I've got to give it a list of edges that will look like 2, 4, 3, 2, 5, 4. And then another list that tells us where to look in the list E to find the start of the edges that originate with each particular node. And so node number 1 starts at position 1. Node number 2 starts at position 3. Node number 3 starts at position 4. Node number 4 starts at position 6. Node number 5 starts at position 6. Because node number 4 is empty, you gotta still put something in there for node number 4, right? For the 4th position in the N list, it's gotta point somewhere. Well, if I say, look, if I tell my computer, look at all of the positions from 6, I want all the positions that are greater than and equal to 6, but less than 6. that's an empty set. And that's exactly what we're doing for position 4 here. We're saying, all right, position 4 can start at 6, but also position 5 starts at 6. So position 4 gets all of those entries between 6 but less than 6. So nothing. It's empty. Okay. List the relative advantages to representing a graph in computer memory using an adjacency matrix and an adjacency list. Consider memory/storage required. Okay. So let's make a little table. We'll say I could use an adjacency matrix. And I could alternatively represent my graph in computer memory using an adjacency list. One of my considerations, almost said considerization. One of my considerations is computer memory. Well, for an adjacency matrix, I have to store n squared bits, right? My matrix has how many entries? Well, there's n rows and n columns, so there's n squared entries. Each one of those is a 0 or a 1, so that's a total of n squared bits. If I have an adjacency list, I have to store however many edges there are, plus however many nodes there are, and those are just integers. They're not necessarily just bits, but they're actually full-on integers. So for an adjacency list, I would need to store m plus n integers in computer memory. The next thing we need to do is, what if I need to check if an edge exists? Facebook needs to do this. If you attempt to look at somebody's Facebook profile, Facebook runs a quick check and says, does the edge exist between Hudson and Carter? And if the edge doesn't exist, then Hudson does not get to look at Carter's Facebook page, right? So social networks got to do a little quick check to see if an edge exists anytime somebody makes a request like that on the website. If I'm using an adjacency matrix, I look up the row and the column and I see if it says 0 or a 1, right? Super duper easy. That is one operation. What if I'm using an adjacency list? Well, I can look up the position in the E list from my N list, where to look. And then once I get to my E list, I have to check. Is that Carter's number? No. Is the next one Carter's number? No. Is the next one Carter's number? No. Is the next one Carter's number? I have to go through the full sublist to figure this out. And so the number of operations is actually the degree of the node operations for checking whether or not an edge happens to exist in that adjacency list. The last thing is, what if I wanted to add a node to the graph? In an adjacency matrix, a node gets added to the graph and I have to put up all of its edges that apply. We're talking about I don't want to lie, but I think it's 2n plus 1 operations. And take this with a grain of salt because I'm not like an expert in computer architecture, right? Like that's not my degree. But I'm thinking about if I just have a matrix written down, let's say it's a 3 by 3 matrix, and I want to add a node. Now I've got to expand it to a 4 by 4 matrix, which means I have to add 7 more entries, 4 across the bottom, 3 on the side. Now it's a 4 by 4 matrix. Hmm? Well, if n is the previous number of nodes, then yeah. If n is the next number of nodes, it would be 2n minus 1. If n is the previous number of nodes, it's 2n plus 1. But yeah. But I'm not really sure how matrices are stored on a computer, really. I mean, that's the thing, is it maybe it depends on what software you're using or what programming language you're using. Because if a matrix is stored in a particular way on a computer where like the second column butts up to the first column on physical memory, then maybe adding an extra row and an extra column means shifting everything. Maybe that means n squared operations. And so, not really sure what this is, but it could be up to n squared operations for shifting all of the data around to accommodate a new node. What about an adjacency list? An adjacency list would only need to put a node at the end and add some edges. This is like degree of the new node operations. It's barely anything, right, to make one of those lists longer. Tell it where to find the new stuff. That's like super easy. So let me put smiley faces and frowny faces. This is a good thing. Because if I have 10 nodes and 10 edges, then 10 plus 10 is 20. But if I have 10 nodes, 10 squared is 100, right? So it's always worse to have an adjacency matrix in terms of memory storage. Maybe not so much at small numbers of nodes because bits are easier to store than integers. Like an integer might take like 16 bits to store each integer. I don't know how many, it depends on how big of an integer we want to store. But what if you are Facebook? How many Facebook users are out there? A billion? Right? What if I have a billion nodes in my social network? What's a billion times a billion?
A lot.
10 to the 18th? We're talking about 10 to the 18th bits. But what if I have a billion users and each user has 200 friends on average? Well, then we're talking about a billion. We're talking about 200 billion-ish. 200 billion is a lot smaller of a number than 10 to the 18. So even though it's a big number, an adjacency list would take up way less memory than 10 to the 18 bits. What about checking for an edge? Well, it's really fast to check for an edge in an adjacency matrix. It's kind of okay in an adjacency list. Like there's nothing bad about that. That's not like a really slow operation. It could be better. It could be optimized with an adjacency matrix, but you know. Adding a node is really bad for an adjacency matrix. And it's by comparison a lot better for an adjacency list. So things are looking pretty bad for the adjacency matrix. The only thing that I would say is maybe it makes sense for an adjacency matrix if you know you're never going to have to add a node. If a system is very, very much a fixed system and it only changes like once a year when you add a new train station, go ahead and use a matrix. But if you are running a social network where you constantly need to be adding nodes, then you should be using an adjacency list. There's one other thing that you could say about this, which is certain computer science algorithms require a little bit of linear algebra for the magic to happen. I'm specifically thinking about Google's PageRank algorithm. Like the reason that Google became a big company in the first place was Google search. And back in the day, search engines on the internet sucked. Like they were just awful. There was like Yahoo and there was AOL and there was Ask Jeeves. But those engines did terrible until Google search came along and Google was just miles and miles and miles better. Everybody used Google and it became a huge company. The reason Google search worked so well is because one of the founders or co-founders came up with an algorithm called PageRank. PageRank requires creating an adjacency matrix for all of the websites indexed towards your search terms. And then it calculates eigenvalues, which is a whole topic we would discuss in a linear algebra class, not in this class. And then using the eigenvalues, it ranks the pages. But you can't calculate eigenvalues from an adjacency list. It doesn't work. You have to create the adjacency matrix before you can calculate eigenvalues. So in certain computer science applications, you have to use the adjacency matrix, even though it eats up a ton of memory and it's hard to add nodes. So can't forget about it. All right. An incidence matrix of a directed graph. I don't think you would use an incidence matrix if your graph wasn't directed. So I think it's pretty much only for directed graphs. It's not the same as an adjacency matrix. What's different about an incidence matrix is that the rows represent nodes and the columns represent edges. A 1 is placed for entries representing an edge entering a node, and a -1 is placed for entries representing an edge leaving a node. So again, I'll try to draw something really quick here. That looks nice. So I'm going to label my nodes. 1, 2, 3, 4, 5, 6. And for an incidence matrix, I also have to label my edges. And when I go to write my matrix, the rows are the nodes and the columns are the edges. So I'm going to come up with the row 1, which is going to be node 1 first. And I'm going to place a 1 if the edge is entering and a -1 if the edge is leaving. The second row is going to be the second node. Edge 1 is going in, edge 2 is going out, and edge 4 is going out. For the third row, it's node 3. 2 is going in, 3 is going out. The fourth row is the node 4, where 4 is going in, 5 and 6 are going out. No, I got my minus signs mixed up there. 4 is going in, 5 and 6 are going out. For node 5, 3 and 5 are going in, and for 6 6 is going in. So in an incidence matrix, you should have the same number of negative ones and positive ones, right? Because every edge should be going in and out of a node, so you should get pairs of negative ones and positive ones. In fact, since every column represents an edge, you should be able to look down the columns and find a negative one and a positive one in every single column. Boom, boom, boom. This is my incidence matrix. And again, you'd only really do this for directed graphs. There is another time in my life where I've seen an incidence matrix. Back when I was working as a chemical engineer, there's this really cool process data reconciliation problem I was working on where you create incidence matrices, again, to represent to a computer what the process flow diagram looks like in real life. And we do this for mass balances. Because all of the material flowing into node 2 should equal all of the material flowing out of node 2 in a continuous chemical process. All of the mass should be conserved. I'm not deleting any mass, I'm not creating any mass, so everything going in has to go out. And so we create an incidence matrix, and it's part of the math behind ensuring that the mass balance is guaranteed and coming up with the flow rates of the materials going around. In the fall, I'm going to offer a class called Optimization Techniques. And part of that class, I'm going to teach all about how to do process data reconciliation. So we'll see that again in the fall, if any of you guys are taking optimization techniques. Okay, a path is a sequence of distinct nodes where each adjacent pair is connected by an edge. A path represents a way to get from one point to another. So these are really formal definitions, but think about path. The word path is exactly what it sounds like. This is a path. 1, 2, 3, 5. Okay? A cycle is a path that starts and ends at the same node. So if I want a path that starts and ends at the same node, maybe my path would look like 4, 2, 3, 5, 4. That would be a cycle. Of course, sorry, that's a directed that's a directed graph, so you couldn't actually do that cycle. But if it was an undirected graph, you get the idea. Starting and ending at the same node. A graph is connected if there exists a path between every pair of nodes in the graph. A path is disconnected if it's not connected. And I feel like it's kind of silly, but this altogether would be considered a disconnected graph. I'm not really sure what the applicability is, or like when does it make sense to talk about disconnected graphs, because if it's not connected, is it really the same object? I don't know. I'm definitely not an expert in every field, so maybe this does have some application. But as far as I know, most useful graphs are connected. All right, Connor. If you are walking around the city of Königsberg, is it possible to cross every bridge exactly once? You can't go swimming. You can't swim through the river. You can only cross a river by crossing a bridge, and you can't go back, right? You can't cross a bridge twice. Is it possible to walk through the city crossing every bridge exactly one time?
I don't know.
Do you know the answer to this? Yeah. Okay. We'll give everybody 2 minutes to think about it, and then we'll take a vote.
Oh! I found it.
You did?
I know where to go.
Show us. Show us. Show us. You can stand up and go to the TV if you want.
Hold on, wait. Yeah. Skinny my way over here. So you start here. You go 1. Oh wait, never mind. You gotta come back. I got it. Okay, never mind. No, I'm wrong then.
Show us, Connor.
I'm wrong. Start up here, go down, cross, up, down. Wait, I definitely had it. Yeah. I think we both kind of right. Up, down. No. Okay, I definitely had it. Shucks.
Oh, wait. No, I didn't.
Nope. Didn't have it.
Nope.
Is it possible?
Oh, I thought I had it for a sec, but I definitely just did it wrong. I think I did.
All right, go sit down. Who thinks it's possible? Raise your hand if you think it's possible to do it.
I think we've all given up.
Nobody? Okay, raise your hand if you think it's impossible. Can never be done. Yep, it's not possible.
You may not swim.
You could represent the city as a graph. And this graph would have 4 nodes. Here's 1, 2, 3, 4. And then the bridges would be the edges between the nodes. And this is like a multi-graph, right? So I've got some parallel edges going on. I'll draw this again when it's not on the map. You can draw that graph down here where you can see it better. So there's like 2 islands and then the 2 pieces of land that are not islands. And I've got like 1, 2, 3, 4, 5, 6, 7 bridges.
Yes.
And the answer is no. Number 1 biggest mathematician of all time, Leonard Euler, figured this out a long time ago. He said, you can traverse a graph that means find a path, I guess. Crossing each edge only once if and only if one of these 2 statements is true. The first possibility is every node has even degree. Or every node has even degree except 2. And this would be your start and end points. In the case where every node has an even degree, the path you're looking for is a cycle, where it starts and ends at the same node. And if every node has an even degree except 2 of the nodes, then that's just a path that's not a cycle, and the start points and end points are the 2 nodes that have odd degree, where the degree is the number of connected edges. So this solves the problem, right? Because if I look at this graph of the bridges of Königsberg, I see that this has degree 3, this has degree 3, this has degree 3, and this has degree 5. So according to Euler's formula, he says this is not going to be possible unless we delete some bridges or add some bridges. So you might be wondering, is there a proof of this formula? And yeah, the proof is basically this. Proof is that like every node needs to be entered and exited. If it's going to be part of this path that goes through the city, it means I've got to get to the island and I have to leave the island by a bridge. If I'm trying to use every bridge only once, that means that every place I visit needs to have an even number of bridges. The bridges to and from, that means the degree has to be even. The exception obviously being the start point, because I'm only going to leave that section of the city. I'm not going to come back to it, so it should have an odd number. And the end point, where I'm only going to end up there as a destination, so I don't need to leave that point. Unless, of course, I'm dealing with a cycle, and if it's a cycle, then the start point is the end point, and again, I need to leave it and come back to it. So that's the idea.